Okay, welcome back folks. So we are now going to try and have a little look at the underlying principle in how I coded this. Not going to actually look at the code, and we're not going to worry about the details because I'm sure many of you are better coders than I am. But I'm going to show you how I encoded this algebraically, and then how that allowed me to finally spot a pattern. There are lots of false attempts, so I'm not going to spend time on it. I'm going to show you the one that worked for me, and then in a future video I'll show you how I handle symmetries. So, what we're looking for is a way of encoding this particular triangulation in such a way that allows me to generate the correct 5 children in the same way systematically. So, the first thing first is how I encoded this. So, what I recorded. I happen to be using Python for my code because it's the only one language I know to any level, and even then it's not a lot of level. And the mechanism I understand the best is lists. So, quite simply, 1 is currently attached to 2 and 8. So, if I make 2 and 8 a list, I know I'm using the wrong brackets because I'm writing it by hand, then that's true. 2 is attached to 1, 3, 4, 5 and 8. 1, 3, 4, 5 and 8. Lovely jubbly. And so on. 3 is attached to 2 and 4. 4 is attached to 2, 3 and 5. 5 is attached to 2, 4, 6 and 8. 6 is attached to 5, 7 and 8. And 7 is attached to 6 and 8. And 8 is attached to 1, 2, 5, 6 and 7. So these currently are separate lists. Because there are 8 vertices on an octagon, there are 8 distinct lists. So if I put that into a list of lists, I now get an object that has 8 things in it, which tells me it's an octagon, and the things in it tell me how it's split up in a way that I can then interpret later. Seeing as we cracked one earlier, if you remember, the cracking process is centers around which things are attached to 8. Well, that's quite helpful because this item here, this list, tells me what it's attached to. And the example I used physically was this, cracking of the 5. So if we try and generate that from here, we might spot some patterns. So, the first thing to notice, or one of the simple things to notice, is that 8 is not attached to 3 and 4. So these two, 3 and 4, will never change. With coding, you've got to be careful whether you're counting 1, 2, 3 or 0, 1, 2. So there's a little bit of thing to pay attention to if you actually want to code this, but the properties are the same, the principles are the same. So node 3 and node 4 will never change in any of the offspring to this shape because they're not attached to 8. So we can always put those in unaltered. Okay. The node we are changing will always end up attached to the same things it was before because nothing there is being broken, and 9 additionally. So in this case we're changing 5. 1, 2, 3, 4, 5. So it gets the same things as before and the extra 9. And that will always be true. So far, so simple. Now this generates some changes now, because there are things below it and things above it. Because we're counting anti-clockwise, the 9 will always appear what I'm considering to be below the 5, because it's on the one side of the line we're talking about. So things that were attached to 8 before, which is these two, further down on the list, will no longer be attached to 8. Those 8s will change into a 9, because this 8 is being split into 2 things. And in fact, realistically, perhaps I should label this as 8 and not have the 8 label there, and you can see the 8 following over. So these things on the left stay attached to what they were, but the 8 becomes a 9. So this becomes 2 with 9, and this becomes 1, 3, 4, 5 with 9. Alright, that's that family. So we've got 8 itself. No, we'll do the ones above. So we've got these two above, so 6 and 7, 6 and 7, and actually you'll see that those are exactly unchanged because the 9 happens below, so this is just taking a thing that was before and moving it, which means all the connections are the same. So this is unchanged. Right, here we go then. Because we've cracked this, what 8 is attached to will change every time, and it will change depending above or below the target. So 5 is our target, 5 will stay attached. That will always be there. Things below 5 are no longer attached to 8 because we put this extra 9 in place. All these things that were lower down than 5 are no longer attached to 8, so they don't join in. They are gone. So these get crossed off and don't join us over here. Things above 8 stay the same, so we still have 6 and 7 attached. And of course, we've split it to become 9. Finally, we've introduced our new node, our new node 9. While 9 will always be attached to the things up to and including the place we are cracking. So because the cracking is 5, these ones that disappeared actually end up over here. So this will be 1, 2, the one we're attaching, so up to and including, so this gets split in 2 ways, and it will always be attached to 8 because it's next to 8. So again, put that into a massive list. This list now has 9 entries in it, which means it's a nonagon, and each of those 9 entries tells us where things are attached. So there's quite a few rules there, but they're all well defined. So to run through them, we've got the things that are below our point of cracking. So in this case we are cracking 5, which is here. So 1, 2, 3, 4. So that's up to and including 5. No, yes, up to and including 5. Everything they're attached to comes with, unless they're attached to an 8, where the 8 becomes a 9. Yeah, that's the same rule across. So that's everything up to and including there in one section. We then have everything 5 and above, excluding n, the actual size of the shape, where everything comes over because they're unchanged. And then we have what happens to 8 and the new node 9. Again, it's to do with our boundary. Because we are cracking this one at 5, this child has something special about 5, so 5 and above come to play, 9 gets added. 5 and below come to play, 8 gets added. So every one of those rules is well defined, and if you can be bothered to work it out, and it took me a little while because again, coding's not my main thing, and I might share some rubbish Python code in the style of Matt Parker to show you how I built this. So from any given existing polygon, we can generate the appropriate child. You run a loop over these and you get the 5 different children. I've just done one to show you the mechanism. And because the great-great-great-great-great-grandparent of all of these is the triangle, you just need to give it the seed. So my first polygon was the triangle, which I'm not going to start at the beginning because I want to build this page, but 1 is attached to 2 and 3, 2 is attached to 1 and 3, and 3 is attached to 1 and 2. So I fed that in as my initial seed, and that generates me the right quadrilaterals, which generates me the right pentagons. I did some saving, some small efficiencies, but I'm sure there's more to be found in exactly how I implemented this. But that is the key mathematical step. So next time I see you, we'll look at how I handled symmetries. Enjoy.